Welcome to Basic Chemistry for Biology, where we break down the tiniest parts of our world so you can understand the big picture in biology. Today we'll cover atoms, elements, compounds, and chemical bonds, all essential for life. Let's start with the basics. Elements. An element is a substance that can't be broken down into simpler substances by chemical processes. Think of elements as the building blocks of everything. Common examples: aluminum, gold, iron, but when it comes to biology, there are 4 MVPs: carbon, hydrogen, oxygen, and nitrogen, aka CHON. These 4 make up most of your body. Now let's take a quick look at the periodic table. This chart organizes all known elements based on their atomic number. That's the number of protons in the nucleus. It might look intimidating, but it's actually a super helpful tool. Elements in the same column or group have similar chemical properties because they have the same number of valence electrons. That's why sodium, Na, and potassium, K, react in similar ways. Both are in group 1. The table also helps us predict how atoms will bond. Metals are on the left and like to lose electrons, while nonmetals on the right tend to gain or share electrons. And in biology, we mostly focus on elements like carbon, C, hydrogen, H, oxygen, O, and nitrogen, N, all right there on the table. Think of it as a cheat sheet for the universe's recipe book. Now that we know what elements are, what are atoms? Atoms are the smallest particles of an element that still have the properties of that element, but atoms can act a little differently sometimes. If an atom gains or loses electrons, it becomes an ion, either positively or negatively charged. And if it gains or loses neutrons, it becomes an isotope. Some isotopes are radioactive, which makes them super useful for things like carbon dating fossils, treating cancer, and even medical scans like PET scans. Next up, compounds. When elements combine chemically in fixed proportions, we get compounds. Water is a compound, so is hemoglobin, the stuff in your blood that carries oxygen. We also split compounds into 2 main types, organic and inorganic. Organic compounds contain carbon and are linked to living things, like carbohydrates, lipids, proteins, and nucleic acids. Inorganic compounds usually don't have carbon. Water and salt are great examples, though there are exceptions like CO2 and calcium carbonate. How do atoms stick together to make compounds? With bonds. The first type is an ionic bond. This happens when one atom gives an electron to another, and they stick together because opposites attract. Like sodium and chlorine forming table salt, NaCl. One gives, the other takes, and they become besties with benefits, chemical benefits. Then there's covalent bonding. This is all about sharing. 2 atoms share electrons instead of giving them away. If the sharing is equal, we call it a nonpolar covalent bond. If the sharing is uneven, like one atom is a bit greedy, we call it a polar covalent bond. Water is a great example of a polar molecule. The oxygen hogs the electrons just a little bit. A single bond means one pair of electrons is shared between 2 atoms. You'll see this in methane, CH4, 1 carbon bonded to 4 hydrogens. Each pair of electrons holds 1 hydrogen to the carbon. When atoms share 2 pairs of electrons, that's a double bond. For example, carbon dioxide, CO2, has a carbon atom double bonded to 2 oxygen atoms. These bonds are stronger and shorter than single ones. Triple bonds? You guessed it. 3 pairs of electrons are shared. Nitrogen gas, N2, is a classic example. This bond is super strong, which is why nitrogen gas is so stable in our atmosphere. So far, we've talked about bonds inside molecules. Now let's zoom out. Intermolecular forces are attractions between molecules. One type is the hydrogen bond. Even though it's weak compared to covalent or ionic bonds, hydrogen bonding is crucial, especially in water. It's what gives water its unique properties like surface tension and high boiling point. Finally, how do we get from molecules to real action? Chemical reactions. These come in a few types. Synthesis, where atoms or molecules come together. Decomposition, where a molecule breaks apart. Single replacement, where one element swaps in. Double replacement, where parts of 2 compounds switch places. These reactions power everything from digestion to photosynthesis. Here's a snapshot of the 4 major types of chemical reactions you'll see in biology and chemistry. Let's break them down one more time, with visuals to help lock it in. Synthesis reaction. This is when 2 or more atoms or molecules combine to form one larger product. Think of it like building a Lego tower, simple pieces coming together. For example, hydrogen plus oxygen, water, H2 plus O, H2O. Decomposition reaction. This is the opposite. One molecule breaks down into simpler parts. Kind of like breaking a sandwich back into bread and meat. For example, H2O, H2 plus O, single replacement reaction. One element swaps places with another in a compound. Imagine someone cutting in to dance with a partner. Example, Zn plus HCl, ZnCl2 plus H2. Double replacement reaction. This is when two compounds switch elements, like two dancing couples switching partners. Example, NaCl plus AgNO3, NaNO3 plus HCl. These reaction types help explain everything from digestion to rust to photosynthesis. If you can identify the type of reaction, you're already halfway to understanding what's going on in the chemistry of life. And that's your crash course in basic chemistry for biology. Understanding these basics will help you unlock how life works at the molecular level. Stay curious and remember, even the tiniest particles can have a huge impact.